wait, Alberto, because you have to also get special cup, of course.
This I will keep this.
And,
For sure.
and you have to drink this. It's equally drinkable. It's a Danish specialty. This is Aalborg Aquavit.
Aquavit.
So you have to hopefully enjoy this in the company with all Maurizio and all kinds of friends. Thank you very much.
You're most welcome, and thanks for the invitation again to everybody in the committee.
Thank you. And
actually, the Aalborg goes into coffee. That's a very good.
so for the final contributions and final invited talk here, it's my pleasure to introduce Annie Liu. Annie has been a very prolific contributor also to PEPM, but has actually over the last many years, that's the reason's history, developed the field of basically incrementalization of programs. So she's worked very intensively in a number of other areas also on combining, again, programming languages with algorithmic ideas, generating very efficient algorithms, and doing this in a systematic fashion, in particular by systematic incrementalization and transformation and semantics-based methods. Welcome, Annie, for your presentation.
Thank you. Thank you for that, Fritz, and thank you for the invitation to speak at this PEPM history celebration. So I have to say I'm speaking on increment computation, but it has a close relationship with partial evaluation in many ways. I have only 20 minutes or something to tell you about incremental computation. If you don't have questions about it at the end, you can ask a lot more about the connections. And in particular, like Fritz mentioned, actually some important this work was published in PEPM. Okay. I have to first apologize, actually. I couldn't be there in person to some issues with travel documents, let's put it that way. As it happens, I'm speaking at Stony Brook University. It's on Long Island, New York. 30 miles east of Manhattan. So let's start. Incremental computation. It studies how to efficiently handle continuously changing input by storing and reusing previously computed results. Okay, so you may see easily that we want the computer programs to handle input from the real world and forward changes. Okay, but what if I just handle one static data? Well, computer programs process any non-trivial data, or especially large data, by iteration or recursion. So computations must be performed on repeatedly changed state. You probably get an idea that's fundamental for every computer program. So indeed, it is fundamental and ubiquitous. Just think of your favorite graph algorithm program. That's probably including everything essentially non-trivial. And including, of course, because machine learning is popular, in the training of neural network, automatic differentiation is the core of all of this. Okay, so here is actually the outline. There are two parts. The first is an overview of incremental computation, 3 categories. And I will say the essence is incrementalization. Okay, and in particular, there's really interesting connections about incremental computation and partial evaluation. Okay. And then the second part is about systematic method for incrementalization. It actually corresponds to differentiation, except you do it in the discrete domain. But also most interesting is optimization, general optimization using incrementalization. It corresponds to integration by differentiation. At the meta level above all of this, I really want to show that high-level data control and module abstractions are really powerful, and they enable the development of new and better algorithms and drastically optimize the programs with complexity guaranteed. Okay. So this is really building on the shoulders of giants, and I couldn't, of course, list even a small portion of it, but these are people did a lot of pioneer work. I'll mention some of them, and of course, and the students who helped make new explorations and funding support. So here is an overview of incremental computation. And I group everything into 3 categories. In fact, I did this 30 years ago, but this time I spent several weeks review the material, and this was confirmed. Okay. So First class is incremental algorithms, and then incremental evaluation framework, and then incremental program derivation method. Okay, so algorithms, well, by the way, in algorithm community, there's things also called dynamic algorithm, onion algorithm, streaming algorithm, sketching algorithm. They all have the same idea. You want to compute some particular function, okay, such as shortest path, and under some kinds of changes, for example, adding, deleting edges. Okay, and you want to do it fast, of course. By using what you computed before, you add and delete some edge. Okay, and of course, in programming languages, we do incremental parsing, incremental attribute evaluation, the more generalized circuit evaluation, constraint solving. Just every problem you solve when input changes, you have to do it. Okay, so these are particular algorithm changes. So if you try to do in general, there are these frameworks. They try to do classes of programs expressed in the framework and handle a class of change. And most basic thing is caching function results. You compute something before, if the function argument didn't change, then you can reuse it. And if there are changes that you have to recompute, you compute those change propagation and various combinations. Okay, and then finally, these are methods trying to derive for each particular problem and each particular kind of change, these incremental algorithms. Okay, and the general methods, tabulation, it's like memorizing caching, but you transform the program to do it. For each program, you do it differently, right? Specialize best for that program. Finite differencing, you will see some of those, and the database view maintenance. So there were just too many. For individual algorithm, actually, the oldest one is probably this, I think it is, tabulating top polynomials by Henry Briggs in the 1600s. And they compute these tables for logarithms. So, right, a polynomial, and if x changes a little bit, what is the new value? And this method was implemented in the difference engine, is credited as the first computer, the Babbage's difference engine. And then actually in the first work on exploring the idea of partial evaluation, actually a general form of partial evaluation, you know some information like x squared m3, and you're trying to use it, it's actually called incremental computer, increment computing, okay, 1964. And then the first one people credit Michi memo functions, okay, they actually published in Nature in 1968. It's called the memo functions and machine learning. Indeed, they just caching function results, and later in the paper, he talked about it, and interpolations, approximations. Okay? And then for transformation, so many as part of this study, actually, I found what's interesting was that the pioneers for high-level programming languages. Lisp started in the 1950s, and that's for first functions, of course. And then Settle is centered around sets. By Jack Schwartz. There's some records says it was started in 1969 because there was a big book of hundreds of pages in 1970. And even John McCarthy and Jack Schwartz actually had the papers on transformations to do essentially tabulation. Okay, both are, I think, informally, let's just Settle newsletter. This was some notes I found only just a few months ago while preparing for this. Of course, there are all these other people did extensive research. Okay, indeed, even 1993, a Popple tutorial, especially giving a categorized bibliography, it already has 117 references. And now it's, I think it was 8,000 when I looked a few years ago, a few months ago, when searching for incremental computation. Okay, so essence of incrementalization. I just need one concept, which is called incremental programs. Okay, given a program F and operation plus a program F prime is called the incremental version of F under plus if F computes fx plus 1 efficiently by using fx. So you really want to compute fx plus y. So you introduce new function F prime, using not only x, y, but r, the previous result. Okay, with that, incrementalization just to compute this incremental version given f and plus. And I say this is the essence. Okay, we'll see. So for the three categories. So an explicit incremental program, as you can see, it is just the same equation we had before, except it's a particular f0, a particular +0, and particular f1. And incremental evaluation framework try to be general. So it is evaluator of some, incremental evaluator of some evaluator. This evaluator, of course, as you know, takes two arguments, which is the function and the data, okay? And it handles some input change. So this is the input change. So the incremental version is the incremental evaluator. It's general because it handles functions, in the language the evaluator handles, okay? But it's also restricted to a particular class of changes that the evaluator handles, not specialized to each particular program. Okay, and finally, the derivation method, of course, as you can see, if fn plus, you want to get them prime. Okay, so how is it related to partial evaluation? Well, partial evaluation, as you were seen already, right? Function, you can think about taking two parts, and then if you take the value for the first parts, you get a specialized function, and that function then takes the remaining arguments and compute the whole thing very efficiently. Okay, and you know this is so fundamental to compilation, but because the idea to generalize and specialize, it's just fundamental. Okay, so let's see more connections. So this is actually really intuitive, right? Even these two names. In fact, in PEPM'23, as I mentioned, there are two tutorials. One exactly titled partial evaluation, and the other one titled incremental computation. And I actually talked about this 2 years ago, right? And the ACM even had them have paper that's called tutorial notes on partial evaluation. This is categorized bibliography on incremental computation. Actually, I don't think there was ever any tutorial before or even after for many years, even invited talks. But somehow that particular PEPM 30 years ago did this. And in fact, interestingly, I mentioned this paper by Lombardi. It was on the general notion of partial evaluation. Well, at least these functions, you know something about input, you try to evaluate on the fly as much as possible. But the paper is called Incremental Computer, and particular 67 paper is called Incremental Computation. And this time I actually also found the earliest reference on database view maintenance, okay, by Peter Newman, okay, incremental computation, okay, but in the paper, he actually called it partial evaluation. All right, so actually the word I like to use, right, incrementalization is the transformation, and specialization, you really think like the transformation. And of course, the math under here, this is the Kleene-Sassaman theorem, and I mentioned this is differentiation, we'll see more. So the more precise comparison, of course, partial evaluation is intrinsic for language processing. It's just very cool, okay? But it can be viewed as a special case incrementalization, where the plus operation is just, you take two parts, you take some arguments, but the first part doesn't change. And the second part is something new. So incremental computation would try to reuse things on X1 as much as possible. That's exactly what partial evaluation does. On the other hand, of course, incrementalization is general for computations, optimizations, algorithm derivation, but it can be viewed as a special case of generalized partial evaluation, because that means you take a program, it takes any information, you try to optimize as much as possible. So you can think you take this information, the X is the plus of some previous thing and the new thing, and the F on the previous thing equals some result. Okay, so the generalized partial evaluation is the almighty optimizer. It's really important to explore the special delta here, right? Special plus operation. Okay, so let's look at the second part now, systematic incrementalization. Okay, so it takes, this, anyway, I did this for recursive functions and this for my thesis. Here is the key idea. It transforms x plus 1 using the result r of x, fx. Okay, and you can already get an idea. This is exactly the whole transformation method was motivated by partial evaluation. You can do transformation, right? Do analysis and transformation. Okay, this is really the most big influence. So this actually has three parts. You use all the results, you simply separate the computation on X from those on Y, right? Here, only thing X, Y. And use equality, X equals Fx. So if you see Fx, you just change that to Y. And this Fx can be, say, written in pairs. You can use parts of it. And Fx can compute things with conditions, so you use it under conditions. And now how to use intermediate result like that, Fibonacci. And it's much harder. But here's the simplification. If you transform the program to save all result in all anything compute intermediate result in the result, and then apply P1, and then delete those now needed for compute the original value. And you can do some smart things to only save those. But anyway, the idea is reduce the hard part to P1. And finally, even harder, something not even in the intermediate result. So here, you want to just look at in here. Something was Fx, from Fx, or intermediate result. There's something on X that wasn't before. That's the candidate observed information. So reduce to P1. And then you just cache all of those and store and use, reduce to P2. Okay, and this was implemented in some powerful system. It's interactive, but later ones, as we see, recursive function is really hard. It's automatic. Okay, so this is the most interesting part. It's really related to differentiation because when we use F prime, the only difference here we have explicit input change. This is saying how change in input is captured exactly. This is exactly how changing output. And of course, there are much more. Okay, to chain rules and so on. The most general information is discrete remains hard, right? Because function has to be continuous for differentiation, but discrete remains are full of holes. But the interesting part is using for optimization. Okay, so if I did have a Fibonacci function, you say after you compute Fn, at Fibn, I'll compute n plus 1. And this method, catch and prove, smartly saying, hey, only the previous one is needed. So I have a constant time to compute Fib prime. Would you do it? Okay, so when you add a loop out of it, to do one at a time, add a linear time Fibonacci. Okay, and this was actually a new road told me in 1992 at the start of my thesis proposal. It only took me 3 years to understand what he meant or why it's integration, because I thought differentiation I was doing was the opposite. So the power is huge. And this is one slide summarizing all of it. So actually 3 steps. Optimization is the middle. So first, you want to determine a minimum increment to take repeatedly. So for Fibonacci, right, why you do plus 1, why not plus 2, plus 3, plus k or minus k? Okay? And then you do equalization, use previous result or even additional value. And finally, you will use data structure to represent them. Okay? And actually, what's powerful, this applies to all different abstractions. Loops array with no abstraction, set is state abstraction, function is the control abstraction, logic rules abstract both data control, and the functions were just hiding both data control and logic abstraction, right? This is like imperative programming, database programming, functional programming, logic programming, and all programming. And then when you have data abstraction, for all of you, see you need I2, right? That's incrementalization. For data abstraction, you need to apply implement sets. Okay. For control abstraction, to iterate towards integration. Okay. And actually, thanks to my former student Tom Rothman, we invented this name because they're really fancy names otherwise. Okay. So here are all kinds of examples people are doing. Okay. And all of these are ours, except these marked with my own page. These are all new algorithms for improved algorithms, improved complexities, and Balpage in particular has all these impressive results. Actually, this work, actually a previous worst algorithm, the proposed problem received the extra award, I think a year before. Anyway, the key idea is all these, oh, by the way, this leads to some new languages. The key idea is set rules, high abstractions are really powerful. Okay, if you sophisticated algorithms, see even these are much longer. For recursion, you do dynamic programming, you're just tabling it, and this was you do everything the same across components. Okay, and finally, this is a review of everything you've seen. Okay, just because there's so many categories, the 3 categories really help help you focus on the keys and identify incrementalization as the essence. And the connection with partial evaluation, there's so much. I cannot say all of the influence I had. I used those books and papers as motivation, especially the analysis to be systematic and automatic. Okay, and then the power of this, of course, to optimization, okay, by doing incrementalization repeatedly. And the whole lesson is high-level abstractions give you all these. Okay, and in fact, the caching part, the iterate, implement, and the work we did on this, and some additional sort of auxiliary optimization were all published in PEPM'. Okay, and here is just an overview of current work. Okay, so for objects, once you have objects, you can be concurrent and distributed, and there's really interesting algorithm optimization problems. And of course, for rules and constraints, it turned out that even the semantics was a hard, challenging issue when you have arbitrary negations and quantification. That's what we have been working on. Actually, we have some nice results there. A simple unified semantics. And of course, our bigger interest, and I really want to get back to transformations a lot more, because I've been doing distributed systems and logic constraints and semantics for the last decades, mostly. But it is the incrementalization that allowed us to do distributed algorithms. It's sort of more effective than actually and define the simple unified semantics. Okay. So of course, we want to do more of methods for now these more advanced algorithms and logic. And of course, even more powerful languages, even higher abstractions. Okay, that's all.
Thank you.
Yeah, sorry, this was...
Questions to Annie?
Hi, Annie. This is Sam Lindley here. Thanks for the talk.
Hi.
You talked about this similarities between incremental computation and partial evaluation. Do you have a formal statement that they are exactly the same thing in some sense?
No, they are not. Here is it. Partial evaluation, as at least commonly studied, right? You have two parts. One part is known, and the other part could be anything in the new. It's a special case of incrementalization.
So incrementalization is the more general thing.
Yeah, if you consider if you only gave two parts, one part is fixed, the other one can change. But I said if you have this notion called the generalized partial evaluation, which you take a program and you take arbitrary information about the program, like x greater than 3, right? I don't know, it's a 5 or 6. And then if you can do a perfect job on that, as I said, it's the almighty optimizer, then you can think incrementalization as a special case of that. Because now the information is just fx, right? X is the plus to something, and one of them has value that can be computed, in constant time, we computed before. But by exploring a particular plus, that's what makes it really, really powerful. Okay?
Thanks.
Excellent question.
This was excellent timing, Annie. Thank you very much. And I know it's not as late with you here, but no, wait a minute, you're 6 hours away, so in the right direction. Right. Sorry. So thank you very much again. And I unfortunately don't have any liquid I can give you via telepathy. Have to do it next time. But I'll, as a session chair, I'll just also take the privilege before I get to lose the microphone to maybe express our thanks as a PEPM' community to Meng and to Gabi, who've been the co-chairs.